Hello, my name is Siri, and this is my project for TMath 207 differential equations on the application of differential equations in electrical engineering, specifically RLC circuits. So firstly, what are electrical circuits? Electrical circuits transport alternating or direct current through closed-loop interconnections between various electrical components. Different arrangements and configurations of these components make different kinds of circuits, and RLC circuits are one of these circuits. The resistor is made of resistive elements, like carbon, for example, whose function it is to induce more levels of electrical resistance than the natural ones that affect the circuits. It also reduces the damping and the resonant frequency in the circuit. A capacitor is an electronic component that stores electrical energy in an electric field. It consists of two conductive plates separated by an insulating material called a dielectric. When a voltage difference is applied across the plates, an electric field forms between them, causing positive and negative charges to accumulate on the plates. The primary function of a capacitor is to store and release electrical energy as is needed in electronic circuits. An inductor is a passive electrical component that opposes sudden changes in current. Inductors slow down current surges or spikes by temporarily storing energy in an electromagnetic field and then releasing it back into the circuit. The SI unit of inductance is the Henry, named after American scientist Joseph Henry. So, an RLC circuit can be configured in a number of different ways, such as series or parallel arrangements of the components. The behavior of an RLC circuit depends on the values of resistance, inductance, and capacitance, as well as the frequency of the applied voltage or current. There are several key properties and behaviors associated with RLC circuits, including resonance, impedance, and transient response. Resonance is a phenomenon where the circuit exhibits a maximum response to a certain frequency of the applied voltage or current. Impedance, which is the overall opposition to the flow of alternating current, depends on the frequencies involved and the values of the R, L, and C components. Transient response refers to the behavior of the circuit when it's subjected to sudden changes in voltage or current, and it typically involves time-dependent behaviors. RLC circuits have a wide range of applications in electronics and electrical engineering, including filters, tuning circuits, oscillators, and signal processing. They are fundamental components in various devices and systems, such as radios, amplifiers, and communication systems. Summing up the voltages around the circuit will result in a second-order differential equation. So, in order to get the circuit equation, firstly we have to look at the voltage of the resistor, which is the current times resistance, and the voltage drop in the inductor, which is inductance times the derivative of the current, and finally the voltage drop of the capacitor, which is 1 over capacitance times the integral from 0 to t of the current. And from that, we get what is called a KVL equation, which stands for Kirchhoff voltage loop. It is the sum of all the voltages in the circuit, which are the voltage drops of the resistance, inductor, and capacitor. We then take the derivative of the KVL equation and we get I double prime L plus R I prime plus 1 over Ci is equal to 0. This is the second order differential equation which explains what is happening with the current in the circuit as a function of time. This step is optional, but I divided everything by L, the inductance, to isolate the second derivative of the current. You can still use the equation without dividing by L. I just did that because sometimes that is easier on the eyes. And another interesting thing to note is that the current through the resistor can be found by dividing the voltage by the resistance. The change of current through the inductor as a function of time can be found by dividing the voltage across the inductor by the inductance. And finally, the current leading to the capacitor can be found by multiplying the capacitance by the rate of change of the voltage across the capacitor with respect to time. So the first step in solving the differential equation is to find the auxiliary equation, which is L m squared plus Rm plus 1 over c is equal to 0. Note that we can always divide by L if we want to have m squared have no coefficients in front of it. The two roots of the solution to the auxiliary equation are m1 and m2, with m1 being equal to negative alpha plus the square root of alpha squared minus omega squared, and m2 being negative alpha minus the square root of alpha squared minus omega squared. Now, alpha is the damping coefficient and can be found by dividing the resistance by twice the inductance. And omega is actually the resonant frequency and can be found by taking the square root of 1 divided by the product of the inductance and capacitance. So, what exactly is the damping coefficient and the resonant frequency? Well, the damping coefficient refers to the process of reducing or dissipating the energy of oscillations or vibrations within the circuit. Damping determines how quickly the transient response of the circuit decays, or in other words, returns to equilibrium, when the input changes suddenly. There are three main cases of damping which we will explore further shortly. The resonant frequency, on the other hand, is the frequency at which an RLC circuit exhibits the maximum amplitude of its steady-state response to a sinusoidal input signal. In other words, its frequency at which the circuit resonates or responds most strongly to the input signal. The resonant frequency depends on the values of the inductance and capacitance, as we can see in the formula on how to calculate it. At resonant frequency, the reactance of the inductor and capacitor cancel each other out, resulting in a peak in the current or voltage amplitude across the circuit. Getting to know the relationship between damping and resonant frequency is crucial in designing and analyzing RLC circuits, especially for real-world applications like signal processing. Depending on the desired behavior, engineers can adjust the circuit's component values to achieve specific damping characteristics and resonant frequencies. So let's shift our focus to damping. There are three main cases for damping within RLC circuits. They are overdamped, critically damped, and underdamped, and all of them depend on the values of the roots of the auxiliary equation. In our first case here, the circuit is overdamped, where R squared is greater than 4L over C. And you can also write that as R over 2L squared is greater than 1 over LC. And the roots M1 and M2 are real, distinct, and negative. The behavior of the current is not oscillatory, and the vibration returns to equilibrium pretty quick, as we can see in this graph depicting an overdamped system. The general solution for this type of system is given by I of t is equal to a e to the power of m1 times t plus b e to the power of m2 times t. Oftentimes, an overdamped circuit is caused by a faulty resistor. In case 2, which is critically damped, the roots of the auxiliary equation are actually equal to each other. In this case, the current returns to equilibrium fairly quickly, in the least amount of time, and there's just enough damping to prevent oscillation from happening. The general solution for a critically damped system is given by I of t is equal to a plus bt times e to the negative alpha, which is just negative RT over 2L. Now, the third case is pretty interesting, as in this case the roots are complex. Here is also where the values of alpha and omega, which are the damping coefficient and resonant frequency, both come into play. The current is indeed oscillatory in this case, and the amplitude decreases exponentially. As you can see in the graph, the amplitude of each wave gets smaller and smaller as t increases, or as t approaches infinity. The general solution to an underdamped system is given by I of t is equal to e to the power of negative alpha times t, multiplied by A cosine omega t plus B sine omega t. We know how to calculate alpha and gamma from the previous slide, and that's how you get the general solution to an underdamped system. So let's start. So now that we are equipped with how to find the general solution, we can now solve initial value problems and find the particular solution. So in example problem 1, uh, in a series RLC circuit driven by a constant EMF, which stands for electromagnetic field, the response of the circuit is given by I double prime plus 4I prime plus 4I is equal to 0, for which the initial conditions are I of 0 is equal to 2 and di over dt at time 0 is equal to 4. So for example 1, firstly, we need to write down the auxiliary equation, which is m squared plus 4m plus 4 is equal to 0. And then we find the roots of that auxiliary equation, and the roots I found were m sub 1 is equal to negative 2 and m sub 2 is equal to negative 2. And here we can see that since both m1 and m2 are equal, the response is critically damped. And our general solution for a critically damped system is given by I of t is equal to a plus b times t times e to the negative 2 times t. And we have our initial condition here, I of 0 is equal to 2, and we plug that in order to solve for a. And then we solve for a, and we get 2 is equal to a. And now in order to find b, we need to take the derivative of I of t. And we get di over dt is equal to 2 plus b times t times negative 2e to the negative 2 times t plus b times e negative 2t. And di over dt at time equals 0 is equal to 4. That's one of our other initial conditions that we were given. And this implies that 2 times negative 2 plus b times 1 is equal to 4. So b is equal to 8. And now that we have a and b, we can plug those in and find our particular solution. And therefore, our particular solution is I of t is equal to 2 plus 8t times e to the negative 2 times t. And when we graph that, we see that our graph is typical of a critically damped circuit system where there is no oscillations. And for example problem 2, we are given if the inductance is 0.2 henries and the capacitance is 0.8 times 10 to the negative 6th farads, determine the resistance R so that the circuit is critically damped. And in order to solve this problem, we know from the previous slides that in a critically damped system, R over 2L whole squared is equal to 1 over LC. And the general solution for a critically damped system is given by I of t is equal to a plus b times t times e to the negative alpha times t, where we know that alpha is the damping coefficient. And first things first, the goal of this problem is basically to isolate R. And in order to do that, we distribute the whole squared to R and to L, and then we get R squared over 4L squared is equal to 1 over LC. And we distribute that 4L squared to the right-hand side of the equation, and we get 2 squared is equal to 4L squared over LC. And then we get R squared is equal to 2 times square root of L over C. And after this, it's pretty much just we plug in our values, and then we get R is equal to 1 times 10 to the third ohms. And our resistance, in order to solve the equation, is 1 times 10 to the third ohms. And for example, problem 3, suppose we have an RLC circuit with a resistor of 0.1 ohms, inductor with inductance of 0.05 henries, and a capacitor of 5 farads with constant voltage. A. Set up the ODE equation for the current I, and part B asks us to find the general solution, and part C gives us initial values so we can find the particular solution. So for example 3, I first stated out all the values that we were given, which is resistance is 0.1 ohms, inductance is 0.05 henries, and capacitance is 5 farads. And I also calculated alpha, which is 1. And then I wrote out the general form of the differential equation. And then I plugged in those values and I got 0.05 I double prime plus 0.1 I prime plus 1 over 5 I is equal to 0. And then I divided everything by 0.05, so I double prime does not have any coefficients in front of it, and the equation is just so much easier to work with. And then I found the auxiliary equation of that, which is r squared plus 2r plus 4 is equal to 0. And our roots are complex. We got complex roots, which are r is equal to plus or minus, sorry, -1 plus or minus a square root of 3 times I. And since our roots are complex, the circuit is underdamped, meaning that we do indeed have oscillations. And the general solution for an underdamped circuit is given by I of t is equal to e to the negative alpha t times a cosine omega t plus b sine omega t. And since we have our alpha and omega values, we can just plug those into the equation and then solve for a and b. So we have our initial condition, I of 0 is equal to 10, and then we plug that into, and we get 10 is equal to a. And in order to find b, we need to take the derivative of I of t, which is this really long and ugly derivative, which is di over dt is equal to 10 e to the negative negative t times negative sine square root t square root 3 plus cosine square root 3 times t minus 10 e to the negative t plus b e to the negative t cosine square root 3 times t square root 3 plus sine square root 3 times t multiplied by negative b times e to the negative t. And once you plug in our initial condition, which was I prime 0 is equal to 0, we just get negative 10 plus b times square root of 3 is equal to 0, and b is equal to 10 divided by square root of 3. So now that we have our a and b values, we can plug that into our particular solution, and then we get I of t is equal to e to the negative t times 10 cosine square root of 3t plus 10 over square root of 3 times sine square root of 3 times t. And when we graph that, we can see that it does indeed oscillate, which is very typical of a um, underdamped system. Sorry. And we also see that as time goes on, the amplitude gets smaller and smaller. And these are my works cited, and thank you for listening to my presentation.